Today we're going to look at what's called intersection of events, that is, outcomes that are common to both event A and event B. The word "and" is going to be a clue for us that when we're trying to find the probability of A and B, we're going to need to do some multiplying. And we have to multiply the probability of A times either the probability of B given A, remember that's a conditional probability, or if my two events are independent, it's just the straight up probability of A times the probability of B. Here's an example. I've got a box that contains 20 DVDs. 4 of them are defective, so that means that 16 of them are not. Now, if I draw a little tree diagram of my experiment here, what I'm going to have is I could draw a good DVD out of the box, or I could draw a defective DVD out of the box. There's 16 good ones to pick from and 4 defective ones to pick from. Now, after I picked my first DVD, then what? Well, if I picked a good DVD to start with, on my second draw, I could also have picked a good DVD or a defective DVD. Now, if I don't replace my DVD, that means if I picked a good one to start with, there's only 15 good ones to pick from the second time. There's still 4 defective ones in there, but I've kept this good one that I picked. However, on the first draw, if I got a defective DVD, then I still have 16 good ones to pick from on my second draw, but I only have 3 good ones to pick from on my second draw, or 3 bad ones to pick from. So the probability that both are defective, that's going to fit this outcome right here, a defective one the first time and a defective one the second time. So my probabilities are 4 out of 20 that I'll pick a defective one the first time, the probability of picking a defective, times the probability that I will pick a defective given that I picked a defective to start with. So there's 3 to pick from the second go around and only 19 to pick from on the first go around. And when we do the math there, we get a decimal number of, I don't know, 3 over 95, whatever that decimal turns out to be. I'll let you guys figure that out. So here's another example of "and." The die is rolled and 2 coins are tossed. What's the probability of rolling a 5 and flipping 2 tails? So the probability of rolling a 5 and the probability of getting a tail and the probability of getting a tail. Now, if all of these are independent of each other, then I just multiply their separate individual probabilities. And they are independent of each other. Getting a tail here has nothing to do with getting a 5 here. Getting the coin to land tails up here doesn't have anything to do with what it did on the prior flip. So there's a 1 in 6 probability of getting a 5. There's a 1/2 probability of getting a tail. And again, a 1/2 probability of getting a tail. So when we multiply all that together, we get 0.0416666666, so I'll just round it to 0.042. Now, this is sometimes called joint probability, and here's these formulas again. Notice that I can come up with a formula for conditional probability by doing a little algebra on this formula right here. So there is a relationship between the two. Sometimes the formula is the way to go. What's the probability that a student is a computer science major given that the student is a senior? So here's how this would look if we wrote it out this way, given that they're a senior. Now, if I look at my formula up here, notice the B's and A's, the order matters. I'm going to find the probability that a person is both, so that's 0.03, that they're a computer science major and a senior, divided by the probability that they're in this second group here, for the probability of A.